Okay. So, we're going to continue talking about covalent compounds. Covalent compounds can be different, right? Ionic compounds totally transfer the electrons away, right? They give them up and you become charged. But what happens when you're sharing electrons? Do you always share equally? Huh? Is the sharing always equal?
No.
No. How do we know if the sharing's equal or not? That's a good question, isn't it? If the sharing's equal, it means something about the compound. If it's not equal, it means something else about the compound. So we have to determine, is it shared equally or not? And the way we determine that is by looking at, I don't know why they have a chart for polyatomic ions in there, something called electronegativity. This chart should be electronegativity. If you open your book to page, you've got the electronegativity chart open. What page is that on?
189.
Page 189. You see some values there for electronegativity. Okay? So, when you look at those values, who has the biggest value? Who has the highest value in that chart? Fluorine. And who has the lowest value? Who's the smallest? Cesium. So, high, low. Have we seen anything else like that before? We see lots. We saw trends like that in the last chapter, right? Okay. What does that mean, that fluorine is the most electronegative? It means it wants the electrons more than anybody else does. So when it forms a bond with somebody else, it tries to pull the electrons towards it more than anybody else does. It's the biggest bully on the block. It's playing tug of war. It's going to win every time. Okay? So, metals have very low electronegativities. Look at these metals over here. They're generally 1 or less, right? What do we say? Metals form ionic compounds because they do what? They just give the electrons up. It's like, oh, there's fluorine, here, take them. I don't want them. So they form ionic compounds. But some of these guys are strong enough to stand up to fluorine, like oxygen. It's not too much different than fluorine, is it? 3.5 versus 4.0. Okay. So, in a nonpolar molecule, shared equally. In a perfect relationship, all the duties are shared equally. Theoretically, right? It's a theoretical thing. Doesn't actually exist, right? We all know that. Okay? Think about it. Where in chemistry is there a perfect relationship? This is a great example. If hydrogen marries itself, what is the difference in electronegativity here? Well, look at your chart. Hydrogen is 2.1, and here's 2.1. So is there any difference here?
No.
They both want those electrons the same amount, don't they? So this bond is said to be nonpolar. Okay? Now, when you look over here at hydrogen chloride, hydrogen is what? 2.1, chlorine is 3.0. What's the difference here? 0.9 difference. This is polar. Chlorine is pulling those electrons towards it more than hydrogen. Or you could say the electrons spend more time on this side of the molecule than they do on that side of the molecule. Okay? Fair enough? Because it has a bigger electronegativity. So, nonpolar covalent bonds occur when there is little difference in electronegativity. Here are 3 examples: nitrogen, nitrogen, chlorine, bromine, hydrogen, silicon. When we take the electronegativity values from that chart and we subtract them, if the difference is small, then the bond is nonpolar. It means the electrons are shared equally. Now, when the electrons are not shared equally, and that difference gets to be from 0.5 up to 1.8, this is now polar. The molecules, the electrons spend more time with the atom that has a bigger electronegativity. Okay? Does that make sense? Okay. Now, when the difference gets really huge, oops, we'll come back to this. When the difference gets really big, it becomes ionic. Okay, when it's 1.8 or more. So, this difference in electronegativity values means that the electrons spend more time on one end than the other. The cutoffs your book gives is 0.4, 1.8. Okay, if it's less than 0.4, 1.4 or less, nonpolar. From 0.5 to 1.8, polar, and greater than 1.8, ionic. I love this picture right here. This is nonpolar, okay? The electrons are shared equally between the two atoms. Now here, the electrons spend more time over here than they do here. So what does it mean when the electrons spend more time? Remember when we had an ion and the electrons were transferred? The one that got the electrons became what? What charge? If you gain electrons, you become negative. So the electrons spend more time. There's a greater electronegativity on this end. The electrons spend more time over here than they do on this end. So we have this notation here. Del negative and del positive. It's a partial negative, partial positive charge. Okay? Now when they get totally transferred, it becomes negative and positive. Okay? This is like my favorite analogy of all semesters. You can pay attention. Okay? Perfect relationship. Electrons are like kids. Okay? In a perfect relationship, the parents share the kids. Maybe they're still married, and they share the duties with the kids. The kids spend 50-50 time with each one. What happens in most relationships? They break up. And the kids, statistics say. And what happens to the kids? Do they tend to spend as much time with each parent? No, it's generally not equal, is it?
No.
Like, I have two kids, they spend most of their time with their mom. So what's happened to their mom?
Wore out.
She's become
Negative.
Negative.
Sure. Stress brought it.
She's negative. I'm very positive. I'm positive she's negative. I'm absolutely certain of that. Okay? Because the kids spend more time with her. She's stressed. She was stressed before. Okay? Does that make sense? If there was a complete transfer of the kids, then she would be always negative, a full negative charge. The more kids she gets transferred, the more negative she becomes. Imagine if you had 6 kids that you took care of all by yourself. Good Lord, you'd be ready for the loony bin, wouldn't you? Okay? Y'all understand now about charges here? So this is said to be polar, this is nonpolar. And as we move forward, this is going to be our favorite polar molecule. What is this? This is water. Water is polar. And we're going to talk about why that's important as we move forward. Okay? So, tell me, are each of these, now look, before you go looking at the chart, you should be able to describe a couple of them on here. Look at C. What do you think about C? Nonpolar, polar, ionic. Why do you think C's nonpolar?
Because it's the same.
Because they're the same, aren't they? That's like being married to yourself. That's okay, huh? There's no difference, right?
Right.
It's exactly the same. Now what about this one right here? Without looking at the chart. What do you have?
You have a metal and a non.
You have a metal and non-metal. What do we know about metals and non-metals? Ionic. All right, so these two I have to look up. Nitrogen is 3.0, oxygen's 3.5. So what does that equal? 0.5. So what do we got?
You're in
Just barely polar, right?
Yeah.
So that's polar. Polar covalent. What about hydrogen and chlorine? We already did those before, 2.1 and 3.0. The difference is 0.9, right? So it is
Polar.
polar covalent, okay? And we're not gonna worry about attractive forces. We'll deal with that later. Nope, don't need to do that. Das ist alles. Meaning, I'm done.